All right, thanks everybody for coming to my talk tonight. This is the AWS Deep Racer Open Source Robotics Showcase. My name's Chris Miller. I have a company called Cloud Brigade, and we do some cottage consulting in artificial intelligence and machine learning. Okay. So about me, I'm kind of known as a crazy idea guy, and I take things to an extreme. So when I participated in the first ever cardboard boat race in Santa Cruz, California, I really overbuilt the boat. It was a good team building session, and we ended up winning the boat race, so I was definitely happy about that. I'm a lifelong engineer. I have started out as a community builder. I was promoted to AWS ML Hero this last year, super proud of that. Also, you can see here my Futurama costume based on the Bender character. It has servo-controlled eyeballs. It has an MP3 player with the Bender sayings, and it plays through a 100-watt stereo system. It's all part of that paper barrel, so just taking things to the extreme. So I also won the 2019 Santa Clara Summit race, the Deep Racer race, and was able to go to reInvent at 2019. And so I started to get connected to the teams at AWS, and so when AWS asked me if I had an idea about using open source with Deep Racer, what does a crazy idea guy do? This. So just a little teaser about what our talk is about today. So along the lines of the crazy ideas, I came up with this idea I called the Poopinator. I had actually acquired a Deep Lens device to be able to prototype a project, and I ended up stepping in something one night when I was taking the garbage cans out, and I thought, geez, I wonder if you could train the camera to detect dogs, but only when they're pooping, and then turn on a sprinkler and shoo them away. And it turns out I was right. And much to my dismay, AWS said, we'd love to make a video about this. Like, really, AWS wants to promote me, correcting bad behavior of our canine friends with their technology. So, a little screenshot from the interview there. All right, so for the uninitiated, I'm not sure anyone here is uninitiated, but tell you a little bit about Deep Racer. It is a 1/18 scale self-driving car. It's really a four-wheel drive truck chassis, an RC car, where AWS took the radio out of it and then put an Intel compute node there. And it's really, a gateway for software developers to overcome that hurdle, that intimidation that I personally felt with learning machine learning. I thought, this has a bunch of math that's going to make my brain hurt. And it turns out it was right. But, who doesn't love programming cars and doing races? And so Deep Racer is really what caused me to get the machine learning bug. And it actually caused me to pivot our entire company. So we've completely leaned into AI and ML. And I just realized that as a software development company, if we didn't embrace this technology, we were going to be left behind and our competitors were going to succeed. All right, so with Deep Racer, as I'm sure you've seen, there's a console, which is really an abstraction of the underlying tools that you use for doing machine learning, like SageMaker. And it makes it approachable, so you can just tweak a couple little things and see your model in action and actually compete in races. So AWS did a great job making that easy to approach. So yeah, the Deep Racer is based off of reinforcement learning, and it uses a reward function to teach itself how to drive. And now the virtual leagues are super popular, especially in COVID, and so lots of people around the world have been competing in races and winning fabulous cash and prizes. So what is Deep Racer open source? The Deep Racer team approached several of us in the community this past year and said, we want to open source the software so that people can do more than just race the car around a track. And the Deep Racer is based off of something called ROS2. It's a robot operating system. And it consists of several software nodes that run in parallel in real time. And they all communicate with each other over a pub-sub messaging system, kind of like MQTT. And so when one node publishes a message, another node can then act on that message, however the robot, whatever it's programmed to do. And it also has a quality of service layer so that, some things are more critical, right? Like steering the car before it crashes into the wall is obviously very time sensitive. So you want to prioritize those nodes over other functions that are less critical. And it has a fancy build system that makes it easy to compile all of your nodes into a functioning unit. So this is a slide that just shows you, it gives you a sense of all the different nodes that are used to comprise a system. There's a lot of stuff going on. Reading different kinds of sensors, there's a web server, there's the ability to navigate the object detection model, lots of interlinked moving pieces. So one of the motivations behind open sourcing Deep Racer is that you need a track to effectively use the car. So, the car costs money, then you need to invest into a track. And so that's a big lift for a lot of people. At the end of the day, it's a robot, right? So you could program it to do other things. And so this was an exercise in exploring that. And the AWS team built some internal projects, and they approached us in the community to see if we had any ideas for things that could be included in this launch. So 3 of us ended up suggesting ideas and built projects, which I'll talk about in a minute. And this is a Deep Racer track, and it was down the hall from my office, and you can just see that's a lot of stuff to have to carry around, a 26 by 17 foot track. All right, so one of the things that I was looking at when I was thinking up ideas was further gamifying the platform, so doing something beyond car racing. So I was kind of inspired by people playing the role-playing games, fancy network games that are popular with all the kids these days. So open sourcing allows more use cases. Things that could be a proof of concept that then can be built on as a concept into real tools that could be used to benefit humanity. I heard someone suggest building a firefighting robot based off of some of the work that we've done, so I thought that was super interesting. So the first project I want to touch on is by Martin Paradisi, who's sitting here in the audience today. And so his idea was to build a better mousetrap, so appropriately named RoboCat. This is a modification to Deep Racer where the object detection model is trained on a mouse, which happened to be, I think, a remote control vehicle. And so as he would drive the mouse around his house, the Deep Racer car would then follow it. And so some of the suggested uses were, doing a better job at pest control. This is another one that came out of this project by Joachim Leuchtenberg. So in his model, he was saying, well, we race the car around a track, but what if we wanted it to navigate through city streets, at 1/18th scale, of course. So he set up a system where the car would be able to understand a stoplight. And so when the stoplight turned red, the car would stop, and when it turned green, it would continue on its way. And in fact, a clip of this was at Midnight Madness. If you saw the Deep Racer car come up to a laptop with a little stoplight, that was this project. So super cool to see that. So my project was called Deep Blaster, and much to my surprise, when they came around to me and said, well, Chris, what idea do you have for Deep Racer that would benefit humanity? And I thought, well, what if we took a Nerf blaster and put it on top of the car, and then we could further gamify the race by requiring that the car would find inanimate objects and assimilate them by blasting little foam balls at it. And they said, think you can get it done in 3 weeks? I'm like, I think so, maybe. It took me a little bit longer than that, but it was a super fun project. It was my first experience with the robot operating system, and it was just a deep dive and just make it happen. Let's see. All right, so I'll just walk through some of the components of the car. I was able to get my hands on the LiDAR bracket model and then make some modifications to that to provide just a foundational base plate on top of where the battery is stored. And then I found this on Thingiverse. Somebody had a toy tank and they wanted to mount a camera on top of it. And so we were able to take this model and modify it and then combine the two together. And this is a 3D printed Nerf blaster. This guy, Luke Goodman, I had read an article 2 weeks before this meeting with AWS, and this guy was into Nerf modding, and I didn't even know that was a thing. And so he started a company, and he was 3D printing parts to modify Nerf blasters. And he now has like a 5,000 square foot warehouse it's full of 3D printers, and he can't make these parts fast enough. And this Jupiter blaster is one of his designs, and I thought, okay, well, if I'm gonna put a Nerf blaster on the car, I've gotta talk to this guy. So I did this emailing back and forth to find out more, and it was really hard to get one in time because they were sold out of everything. And yeah, so this was super cool. And so this is what the car looks like, almost completely assembled. So I'm still working out some of the soldering and where I'm gonna put some of the components, and you can see on the back there, there's an Arduino, which was a key piece of functionality that I'll get to here. So this Arduino, I'm calling it the blaster controller, and one of the first limitations that I ran into with the Deep Racer car was that it only has two digital I/O ports that are set up with what's called pulse width modulation, which is what you use to control the steering and the throttle of the car. So I had to find a way to extend it so that I could put at least one more servo motor to be able to aim the blaster left and right. And ultimately, I want to add another servo to be able to point it up and down so I can really hone in on the object with the object detection model. So what I did is set up a serial communication link between the Arduino and one of the USB ports on the compute node, and established a protocol, which I'll tell you a little bit about here in a second. And what this allows you to do is to be able to extend the platform. So it's not just that I wanted to add a couple of servos. I look at the Fukushima nuclear incident, where they had to send a robot in to detect the radiation levels because it wasn't safe to send a human in there. Well, in this case, you can add sensors to this Arduino and then send that data back into the raw system and then act on that data. So I thought, if I'm gonna do this, even if somebody doesn't want to build a deep blaster, this one component is key to being able to extend the platform to do other things. So super proud of that. Also, we use the Intel Neural Compute Stick. That's kind of the brighter blue thing that you see there next to the Arduino. And it's a coprocessor that makes it easier for the car to process images. There's no GPU on the Deep Racer compute node. And so it can only do so much. It can only inference so many frames per second. And so if you offload that inferencing to the Neural Compute Stick, you can inference a faster frame rate, you can do multiple cameras. So I would say, if you were to try this at home, kids, I would get the Neural Compute Stick for sure. All right, so I mentioned some of the limited I/O ports. There's actually 5 that are available. 3 of them go to LEDs on the car. So, there was a chance we could desolder an LED, but I didn't really want to permanently modify the car. There are 5 USB ports, so if you get the Deep Racer Neo that has 2 cameras and it has a LiDAR sensor, you're already using most of the ports. So that's I was a little bit concerned about not having enough ports, and maybe I should use Wi-Fi with the Arduino or even Bluetooth, but I thought, it's inherently unreliable. you're always running into problems with the Wi-Fi, interference from other access points and stuff. And so serial is not the fastest, but it's definitely rock solid. All right, so this is a representation of kind of how everything fits together here. So we've got the Arduino MKR is what I used, but the Arduino Nano Every is a smaller unit. It's even less expensive. So pretty much any Arduino will work. The Jupiter Blaster has its own LiPo battery to power it, so we're not sharing power with the car, which is a good thing. To control those motors, they actually have a 28 amp current at stall. So if you end up jamming a Nerf ball in between the flywheels, you can actually start melting wires and stuff. So switching that kind of load, that's a critical consideration. And so originally I was looking at doing it with relays, but when you get into like 30 amp relays and switching that kind of current, you really run the danger of burning out something on the Arduino or taking out your compute node. So I use something called a MOSFET. And there are two of those there. One controls the flywheel motors that ultimately blast the ball. And then they also control the feeder motor, which is what feeds one ball at a time into the flywheels. So MOSFETs are used in a lot of analog audio equipment because you're dealing with high current. And they just happen to be a perfect way to switch high loads with something that's relatively fragile like a Arduino that's running on 5 volts. Okay, as I said, the Deep Racer is based off the ROS operating system. When we were pulled in to work with this, we were provided with some sample projects, and there was one that I liked. It was called Follow the Leader, and it most closely resembled what I was trying to accomplish. So what I was able to do is basically make forks of the code of 5 of the different nodes to be able to build this functionality. So I made a copy of the object detection node so that I could run my own object detection model if I wanted to do something other than detect a soda bottle or a coffee cup or one of the 90 things that are built into that. The Deep Blaster targeting node is used to communicate with the object detection model and to ultimately aim the blaster in the direction of the object that it's detected. The Deep Blaster control node is what talks to the Arduino, and I could have built this functionality into the targeting node, but again, I wanted that to be a separate standalone piece of code so that somebody could just take and run with that to build something completely different. The Deep Blaster interfaces node is responsible for setting up the communication messages that are passed between the nodes. And it also manages services. Like, so if I wanted a disarm and an arm function, you would do that within the Deep Blaster interfaces. And then lastly, the Deep Blaster launcher is actually a script that is responsible for making sure that all of the nodes come up in the right order and everything is running perfectly so that the car can do its thing. So this is a representation of the node workflow, and all of this information is available. All of these projects that we've done in the community are open sourced, and this documentation is on there as well. So here you can see the communication flow between the different nodes and how the car communicates with the physical controller and deals with the servos and turning on the flywheels of the blaster. So this is what I call a static action space. So in this version of Deep Blaster, it is using the existing built-in camera. The camera is fixed at the front of the car, so the camera itself doesn't turn. If the car turns away from an object, at some point that object's out of view. And so there's a limitation that the blaster can only aim at things that are within the field of view of that main camera. And so I set up 5 discrete positions where if you move the object to the left and the right in front of the blaster, it will turn and aim in the general direction of that object. And this was partially done due to time constraints with the project. The future plan is to add something called a dynamic action space, where there's a second camera that's mounted on top of the blaster, and it can independently aim at an object, use a separate object detection model so that the car can actually race around a track and pass an object that it might want to blast a foam ball at and independently turn and aim at the same time. And this is just another representation of kind of how the static action space works. Okay, so I'm going to get into some of the technical design considerations that went into this. So with serial communications, I talked about Wi-Fi not being stable. There's no standard protocol for the communication. So you could echo words or characters and have something on the other side listening for those characters and act on it. But with serial communications and building your own protocol, you're responsible for doing things like error correction, like what if it didn't understand the command that was sent, acknowledging that it's received a command and actually acted upon it. And, it's not fast, but it's fast enough. So I didn't want to reinvent the wheel, and I found a library called Robust Serial, where this guy, Antonin Raffin, created this nice protocol that was extensible and would allow us to operate up to 255 commands. And it had Python and Arduino examples. So it had code that would drop right into the Arduino. I had Python code I could test as I was doing my build, and then ultimately integrate that Python code into the node, the blaster control node, which was also written in Python. So that was super convenient. The next thing is the servo control. So if you recall, I mentioned pulse width modulation is what's used to control a servo. And so it basically sends a square wave to one pin on the servo, and the servo knows to steer to a particular direction based on the pulse width of that signal. So the problem is that when you set a certain pulse width, that servo will just race over to that location as fast as it can. And my concern here is that with the car moving around as it is, the camera vision can get blurred, right? It just gets really jerky, and the object detection model might not be able to accurately detect anything in that frame if it's all blurry, right? So I knew moving the servo as fast as you could was probably not the answer. Another way that you can do this is you just use a counter and you loop through and just gradually increase the pulse width until the servo gets to the location that you want. Problem with this is called sweep positioning. You can see it's very slow. So I needed something that was better than this. It was kind of a middle ground, something that understood, I need the servo to get here, I need it to get there in approximately this amount of time, and I don't want you to accelerate or decelerate greater than a certain speed to get there. So this would provide a really smooth action for rotating the turret, for which that second camera would be sitting atop. And so again, why reinvent the wheel? So this guy, Simon Blewett, went through and did all of the hard math that I don't particularly enjoy, and built this library to solve exactly this problem. So I was able to munge the Robust Serial library along with the precision servo control, and that ended up working for us. Oops. All right, so what's next? The turret actually uses a very small servo with plastic gears, and it ended up being fragile for as much weight is sitting on top of this turret. So currently we're working on a new 3D design that uses a full-sized RC servo that has metal gears, and I'd hoped to get it done before I got here, but it is coming, and so that'll be one of the next mods that we make. We want to make it a one-piece design. This is very much a rapidly built prototype, so we bolted it together with nuts and bolts. This whole assembly weighs a lot, and so we need to do some things to lighten the weight, and I've talked to Luke Goodman about having a lighter blaster, and it turns out he's designing one that's meant to be like wrist mounted, and so it'll be smaller and lighter weight, and so that should definitely help. Turret mounted camera we talked about, and if you get the Evo kit, it has 2 cameras in there, so it's just a matter of putting the second camera on a little USB port on top of the turret. And I thought it would be cool if the car could keep track of what it was doing around the track. So as it assimilated these inanimate objects, it could keep track of how many it successfully did that. All right. Does anybody have any questions?
Yeah, if you had a second camera, does that slow down the image processing on that?
Yes, it would on the node itself. That's why I recommend the neural compute stick, because it has the processing power to be able to not only handle 2 cameras, but to be able to provide a higher frame rate. So I don't know what DeepRacer does out of the box. I want to say it's probably something in the order of like 5 frames a second. You know, you don't need to inference 30 frames a second for this. I mean, it would be nice if you could, but at a certain point, it's not really going to add much value. Okay.
Yeah.
So 15 frames a second is what DeepRacer will inference with a single camera. What about with 2 cameras? Okay. Any more questions?
Golden opportunity, guys.
Would you like to see the Deep Blaster? I brought it with me. All right, I'll just set it here on the stage if you'd like to walk up and take a look at it. And this is a standard Nerf blaster, their rival line. It's a magazine that has these little foam balls, which yeah, so here we have links to the Deep Blaster page on our website. I wrote up a blog article to kind of tell the story about how this all unfolded, and it's got some other pictures and video. And the GitHub repo is out there. So you can download this and modify it and make it your own. And if you'd like to connect with me on LinkedIn, there's a link to my LinkedIn profile. Thank you, everyone.